I just want to make sure that I say a couple of things about independence so that we finish off this section. So in 1.6, independence, what was the idea of independence, or what was the way that we could check whether or not we have independence?
That the probability of something given something else is just the probability of something.
Yeah. So the probability of okay, so say that again.
The probability of A given B equals the probability of A.
A given B is equal to probability, right? So knowing that information doesn't change anything. Yeah, probability of B given A equals the probability of B. And then both of those things went together for what formula? What was sort of our, and it's a nice way to check it.
The probability of A and B equals the probability of A times B.
Yeah, the probability of A and B equals the probability of A times the probability of B. Both of these things can be rewritten in that form. Okay. So, I mean, honestly, if you ever want to show independence, showing any one of those is fine. It's fine, right? But oftentimes when we use this idea of independence, we'll use it here. And it's not because we want to show things are independent. It's because we oftentimes will know things are independent, or we will assume that they're independent. That's a nice thing in math. You can always just assume things. It might not be a good assumption, but if it's true, then you can say certain things. Of course, if it's not true, then your answer, your reflection of the real world will be off. How about it? Say it that way, right? And so oftentimes we'll just assume independence, and we'll want to calculate probabilities. And so then toward the end of the class, we talked just very briefly about this idea of if we have 3 or more events, right, we can use this term, say they are mutually independent and again, we could write some conditional probability statements here. If A given B intersects C, or if A intersect B given C, if the probabilities are what we expect them to be. All right. The other way we think about it, again, because this is typically how we want to use this, if the probability of A intersect, I'll write down 3 things, B intersects C is equal to the probability of A times the probability of B times the probability of C. And so, just to point out, and this was an example, and I think we discussed this at the end of class. In fact, there's an example in the book in 1.6 where if we flip a coin twice, and H1 is the number of, H1 is the event in which the first result was a heads, H2 was the event where the second flip was heads, and E was the event where exactly one of the flips is heads. Then you can show that H1, H2 are independent, H1, E are independent, H2 and E are independent. Right? That they're what we would call pairwise independent, but they're not mutually independent. Right? Because the intersection of those 3 things, getting heads on the first, heads on the second, and exactly 1 head, right? The probability of that is 0. We get the at least head. Yet, the probability would be 1/2, 1/2 times 1/2 on the other side, and 1/8 is not equal to 0. Okay? So things can be pairwise independent without being mutually independent, but oftentimes, unless we're setting things up that might have a dependence between them, they will oftentimes pairwise independence will also mean mutually independent. So for instance, if I flip a coin 3 times, and H1, right, heads on the first, heads on the second, heads on the third, right, then it's saying I can compute the probability by computing the probability of heads on the first, heads on the second, heads on the third, right? I can calculate that using multiplication. So, let's see which example do I want. So let me just go with an example. Let me leave it up here because I may come back to it a little bit later. If I flip a coin Nope. Do I want to flip a coin? No, I want to roll a die. Gives me different probability. I don't have to say weighted coin. I'll roll a 6-sided die 12 times. Okay. And I'm going to count the number of 6s that appear. Okay. And A0 would be the result, no 6s. Let's make it a fair 6-sided die. So the probability of any particular number would be 1/6. Okay. I'll let A1 be exactly 1/6 appears when I roll this thing 12 times, and A2 will be exactly 2, and we'll stop there. So let's go ahead and compute that, right? And so the important thing here is now, when I roll a die, when I flip a coin, when I go through certain little sort of sub-experiments on my way to my big experiment, I can safely assume here independence. By the way, it's not really an assumption here. I mean, as far as I know, there's no quantum theory that says a dice's rolls is somehow linked through time and space to previous rolls. Right? It really, I mean, somehow I'm sure this could be formulated, but there really are independent. I don't expect the first roll to impact the second roll to impact the third roll, and so on and so forth. But other times, for instance, when you're going to see, if you're following the news at all, there is a presidential election coming up, right? And when somebody goes out and takes a poll, they go ask people, who are you going to vote for? And there is an assumption in that when they ask one person who they're going to vote for, is going to be independent of the next person, right? Is going to be independent of the next person. So the question then is, have you done your due diligence in terms of trying to make sure that independence assumption is valid? Because if someone were to say, okay, I'm going to go poll 900 people, because that's what you do in a poll, and I'm going to go to the Hillsdale College campus and I'm going to ask them who they're going to vote for, that could look very different than what would actually happen in the nation as a whole, right? Why? Because you wouldn't necessarily have this assumption that you're on the Hillsdale College campus would be independent of the person that you're going to one would end up voting for, right? And given that extra information that I just asked students on Hillsdale College campus, might lead the probability of voting for Biden or voting for Trump to actually change from the population as a whole, right? So sometimes it really is an assumption of independence, and if the pollster does not take care, right, to try to make sure that independence assumption is as good as possible, it's going to lead to problems. And people have argued that's what happened 4 years ago, when most of the pollsters thought Clinton was going to win, but they didn't. I mean, the argument was they undercounted the rural vote, right? So they really made it look as independent as possible, even though that's what they were aiming to do. So. With dice rolls, with coin flips, we like those because that's easy and it's a safe assumption. But with a poll, it really does matter who have you asked, how have you set this thing up so that's a good assumption under independence. Okay. So now let's just answer this question. Okay, so I roll a 6-sided die 12 times. Let's compute the probability we get no 6s. Which is going to mean what then, right? What does it mean to have no 6s?
Every roll is a number between 1 and 5.
Every roll is a number, right? And so there's a couple ways I could write it. Ultimately I won't want to write it out this way every time. But let's just say n sub I is a not 6 on the ith roll. Right? N sub I, what do I mean by that? That's the event where I get a not 6, a 1, 2, 3, 4, or 5 on the ith roll. I could use the complement too if I wanted to, but the complement of 6. So it's really just saying I have a not 6 on the first roll, and I have a not 6 on the second roll, and I have a not 6 on the third roll, and I have a not 6 all the way up through the 12th roll, right? And if this is a good assumption in terms of independence, then it's saying I could take the probability of getting a not 6 on the first roll, and then multiply it by the probability of a not 6 on the second roll, multiply it by the probability of a not 6 on the third roll, and keep that until I get up to not 6 on the 12th row. Okay. Now what is the probability of a not 6? 5, 6. There's 5 not 6s out of the 6 total numbers. So I'd have a 5, 6 times 5, 6 times 5, right? I would have 12 copies of 5, 6. I would have 12 copies, oh, I might break this up in a little bit, so let me turn that one on. Right, so that would be the final, the probability would be 5, 6, right, all not 6s, right, to the power of 12. And if we want a number on that, I do have a number, it's about 11.2%, so it's approximately 0.112. That is, I would expect that to happen 11.2% of the time, approximately 1 in 10 times. I rolled a fair 6-sided dice 12 times, about a little more than 1/10 of the time I would expect to not see any 6s. Okay. Right. So again, I'm not showing anything's independent here. I'm assuming it's independent, and it's helping me calculate this probability here, right? And it says, okay, to turn the probability of this first roll and second roll and third roll and fourth roll, so on and so forth, into a product of numbers. Okay. Let's go ahead and do A1. It's the same. I'm going to do the same thing. What's the probability of getting exactly 1, 6? And maybe here's where I start laying it out a little bit more. I don't know if that's 12 or not. Okay. So then how do I get exactly 1, 6? Well, if I get exactly 1, 6, right? And the other ones are not 6s. So there are multiple ways of doing this, right? I could get a 6 in the first spot, and then a not 6 in the second, and a not 6 in the third, all the way up to a not 6 in the 12th spot. That's one way of doing it, right? Of course, that 6 doesn't have to be the first roll. It could be the second, it could be the third, it could be the fourth, it could be the fifth, right? It could be any of those, right? But here's one way I could do it. I could do it with a 6 in the first, and a not 6 in the second, and a not 6 in the third, all the rest of the not 6s up to 12. And what would be the probability of that happening? Of getting a 6 in the first, and then a not 6 the rest of the time?
So 1/6 times 5, 6 to the power of 1.
Okay. Times 5, 6 times, I'm just going to write them out here, all the way to 5, 6. Okay. Which, for this is just one case, right? Where the 6 is actually the first one, right? I get a 1, 6, and then the rest are 5, 6. And under this assumption of independence, right, that I can compute the probability just by multiplying those things together. Okay, again, and that's a fair assumption in this case. And so it would look like, 1, 6 times 5, 6 to the power of 11. Okay. But that's only one case, right? So how many different cases are there in doing such a thing? 12, right? And how can I see that 12? Well, it could be in any one of these positions. So I'm going to think about it this way because it's going to help me with my next question. I have 12 positions here, and I want to choose one of them to be my position for the 6. Well, I only have one, so order doesn't matter. But if I had 2, right, it just means if I pick position 5 and position 3, that's the same thing as picking position 3 and position 5. Okay. So I get a 12. Why do I get a 12? Well, because I have 12 positions, I could put that 6 in. Or I think of it as I have these 12 positions, and I'm going to just choose one of them to be the position for the 6. And so that gives me this 12 choose 1, which is equal to 12. And by the way, if I want an approximation for that, I can get that, right? 26.7, 0.267 approximately. Okay. So a little more than a fourth of the time, right? A little more than a fourth of the time, I would expect to see, when I perform this experiment, to see exactly 1/6. That's quite often. Okay. Not 2 6s, not 0 6s, but exactly 1/6. Okay. So again, we're not showing things are independent, we're assuming they're independent, they're helping us with our probability calculations. That's how we typically use this. And that's why we like this formula, or sort of this formula most often, because that's going to help us calculate the probabilities we're looking for. Let's do the last one here, the A2. Right? So again, I'm not even going to draw any diagrams here. So what changes with this for A2, the event in which we get exactly 2 6s? Changes in any of this? You guys can speak up, just because you're not wearing masks and hiding anymore doesn't mean. So what changes? Someone else. Yes?
Yes, 2 of the slots become 1/6, and it's 12 choose 2 instead.
So I'll just pick a case, those two, I'll just say the first two, what's that two, right? Let's just say the first two are 6s, and then the rest are not 6s. But then we have to figure out how many different ways we can reorder those 6s. And so that changes that to a 1, otherwise everything else looks the same, similar for that case. Okay. Which means we would have 1/6 squared, 5/6 to the 10th, right, would be the number of ways in which that particular case could occur. But now we have 12 positions, right, 12 flips, and I want to choose 2 of them to be the 6s. I bet you can guess how to do 3, right? We're not going to do that, but. Right. And so then it would, oops, I said 3 and I wrote 3. Right. 12 choose 2, right? We're going to pick the slots that are going to be the 6s, and then everywhere that was a 6, it's a 1/6. Everywhere that is not 6, it's a 5/6, and I go ahead and multiply those. I have commutative properties of multiplication, so I can regroup them, and I get something like that. And this was 29 point something. 29.6 approximately, right? 0.296. Okay. So a little more often, I would expect exactly 2. Okay. And from there, it's probably going to start decreasing. Not probably, right? But yeah, if I had written down A3, it would have been 12 choose 3, 1/6 cubed, 5/6 to the 9th. Right? Where I have to pick 3 positions out of the 12 to be my 6s, exactly 3, right? 3 out of the 12 to be 6s, and then what's the probability of getting a 6? 1 out of 6. There's 3 of those. What's the probability of getting a not 6? 5 out of 6, and there are 9 of those, right? The remaining flips, right? And if I multiply all those things, I would get a value. I guess if I wrote it up there, I better do that. 9 and 3 and 3 there. 19.7.197. So approximately, this is closer to 1 out of 3. This is closer to 1 out of 5. Okay. Of course, what would be the probability of getting all 6s? Roll a die 12 times and getting all 6s.
1 over 6 to the 12?
Yeah, 1/6 of the 12th power, right? Which is very unlikely to happen. Right? Very 0.0000, I don't know how many zeros, and then maybe we'll get something after a while. Okay. Almost impossible. But you roll a die long enough, you might get a string of 12 6s in a row. You do it long enough. All right, so that's the idea, right? That's the idea with independence. The book goes through a couple of sort of just quick examples. They go through one where there are these circuits, right, where maybe you have, I don't know, some sort of fuse here. And each fuse has a certain probability of failing. So this is fuse 1 and here's fuse 2. And let's say the probability of fuse 1 failing is P, and what's the probability of fuse 2 is failing is P, some value P. If you need a number, how about 0.1? They fail with a probability of 0.1. And then in this situation, you can say, well, the system fails if both fail. Right. So think about one of them as giving a redundancy. So if one fails, it can still, the system can still work in the other direction. Okay. It's not until both of these things fail that the whole system would end up failing. Okay. And then the question would be, what is the probability that the system fails? Now, here, we will assume independence. Is that a good assumption? Maybe, maybe not, right? There might be a reason why one is going to fail. That would lead the other one to fail. Maybe if we're talking about fuses, maybe those fuses were made in the same factory and they just have, there's something that happened, that occurred in the production. They were right next to each other in the assembly line and something had gone wrong at the same, close to the same time. And it could be that they're linked together, right? And if they are, it changes the whole thing. But if we can assume independence, right, then the probability the system fails would be the probability the first one fails and the second one fails. Which would be what? What would that probability be? I can assume independence. I can just do a multiplication problem, which would be 0.1 times 0.1, and that's 0.01. So it would fail about 1% of the time. By the way, what if it was that situation I just said? What if they were produced right next to each other in terms of an assembly line, and if one failed, I knew absolutely the other one was going to fail? Then what's the probability that the system fails?
0.1.
0.1. Yeah. If they're completely dependent on each other, right, it would be 0.1, right? Because I know as soon as one fails, which happens with probability 0.1, the other one has also failed. Insurance companies get into trouble doing this, right? Because you assume independence when you should, right? You try to end up with independence of insurance policies, right? If you're an insurance company that specializes in flood insurance and you only sell flood insurance to people along the Mississippi River in particular cases, that's a bad move, right? Because if one person floods, everyone floods, and it changes, right? It changes how likely something is to happen. Actually, what we'll see later in the semester, it generally doesn't change the expected value, but it changes the variance. So either it doesn't happen or it does happen, but when it does happen, it's a huge catastrophe, right, for that insurance company that now has to insure all of this damage. Okay. On the other hand, the other extreme of lack of independence was, what if I knew that when one of them failed, the other one absolutely was not going to fail? What would be the probability the system would fail?
0.
0. Right? Right? I don't know under what circumstances we could say, one of them failing absolutely meant the other one didn't fail. But that would be the other extreme of lack of independence, where then there would be no possibility of the system failing because they both couldn't fail at the same time. So if they were synced so that one failed, the other failed, we'd have a 10% chance. If they were completely opposite, that would be 0, and under independence, it gives us a 1%. Right? So everything else would fall between those two extremes, and independence gives us a 1%. Okay? So there's an example, right? And again, right, we make this assumption in a lot of problems we do, but it's not bad to stop and think about what that assumption means. right? And in a case like this, it means they weren't produced in the same factory, right? Or they weren't produced at the same time, or, there's nothing that can link those things together. And sometimes that's a little more difficult to justify than other times. Okay. The other, and this will be my last example on this in this circuit, is a different circuit. So instead of having them parallel circuits, you could have them in series, right? So fuse 1 and fuse 2. And here, the system fails if either. Right? Not if both, but if either one or the other fails. Oh, think about dying batteries, right? We often try to put batteries in sequence in this way, right? And if one of the batteries is dead, then the thing doesn't work, right? So you don't always have to replace both of them at the same time, although oftentimes one isn't very far behind the other, right? And so that's a little different. It's like the system will fail if either of those fail, right? So what is the probability the first one fails, not or the second one fails, right? Where this one only failed if they both failed, the first one failed and the second one failed. So what would be, if I have the same probabilities, these same probabilities again I'm working with here, how would I calculate that? And again, I'll assume independence. What do you think? How do I compute that one? Because I don't have a formula for independence that tells me how to compute probabilities of unions, except what do I know about the probability of A union B? How else can I write the probability of A union B? Go ahead.
Isn't it probably A is probably B minus the union the intersection of A and B?
Yeah, right. Because when I compute the probability of A and I compute the probability of B, and I add those together, I will have double counted the intersection if there is any intersection. And therefore, I have to subtract off, right, the intersection once so that I'm not double counting it. So that, I'm counting all of A and then I'm counting all of B without the intersection would give me the, the MasterCard shape out of my Venn diagram there. Okay. So in general, that's certainly a rule. I mentioned before, if the intersection is the empty set, that's nice because I can forget about that and I can compute the probability of the union by just adding those things together. Okay. So what changes here with this problem? Well, the probability of a failure in the first slot is 0.1. The probability of a failure in the second slot is a 0.1. And then I want to know the probability of the failure of both of them at the same time, which is a 0.01, right? It's the product of those two things. It's a 0.1 times a 0.1. So in general, I have this formula. If I can assume independence, then this becomes the probability of A plus the probability of B minus the probability of A probability of B. Okay. That does not work in general. That only works if we have independence, right? Then we can say we can compute the probability of that, and it's just the intersection. Okay. So it'd be 0.1 plus 0.1 minus the intersection would be 0.01, which seems like it's going to be 0.1. So the thing would fail 19% of the time. Okay. And of course, we could do this for multiple. I mean, it doesn't have to just be 2 fuses, 3, 4, 5, either in series or circuits. And the book gives some examples of this when you when you mix and match these things also. But if we assume independence, the big thing about independence is when we start looking at intersections, we can calculate the product of A intersect B by multiplying the probabilities of the independent events, and that's going to be huge. It's going to make life easier in some cases, and it's going to be incredibly important to answer certain types of questions. There are certain times when you absolutely want to make sure you have either independence or something as close to independence as possible. If you want an accurate poll, right? If you want to run an insurance company, right? I mean, there are times in which you definitely want to make sure that, you know, you don't have this catastrophic failure in whatever it is you're trying to do. Okay. So, I guess that's all I wanted to say about independence. Are there any questions? Left 20 minutes. Any homework question, anything from the first chapter that people want? We're basically done now. Not basically, we are done with the first chapter. Yes?
I mean, kind of going off of the circuit problem, I had trouble figuring out 73, especially, like, figuring out kind of that, like, at least 4 out of 6, or, I mean, at least N out, or at least K out of N. How to compute that?
So a system has n independent units, each of which fails with probability p. The system fails only if k or more units fail. What is the probability the system fails? And again, we're told that they are we told independent units. Okay. So I have my unit 1, unit 2, unit 3, unit n, right? So I have these different units. Each will fail, right? If we're talking about fail, the probability unit 1, and I'll just say fails, and actually unit I fails, is p. And so let's see, what are we being asked? The system will fail only if k or more. Okay. So if I'm in a situation which, let's see, I have failure here, I can have failure in the first k, right? And then, what do I want to call it? Lack of failure. Success, right? In the k plus 1, where it doesn't fail. Here, not fail. N. That's all. N's always a good one. Not fail. Not whatever it is you're interested in. And capital N, little n, right? So would this lead to a failure, or would this lead to a success? With a system failure or a system success? Okay. This would be the case of exactly k failures. Is that the same thing as a system failure, or does that lead to a system failure? Which does lead to a system failure. Whereas if I would have just had one fewer, right, then it would have been a system, everything would have been fine with the system. Okay. So that's a system failure. Exactly k failures, exactly k plus 1 failures, that would lead to a system failure. Exactly k plus 2 failures will lead to a system failure, right? Everything else up to n, exactly n failures, if everything fails, then it is a system failure, right? So all of those things would lead to system failure, right? Okay. And anything else would not lead to a system failure, right? If I had k minus 1 unit failures, it would not be a system failure. K minus 2, 1 failure, as long as k wasn't 1, right, would not lead to a system failure. It would just be those things here. So let me just say, it would be the same as asking this over here. What is the probability of rolling at most 2 6s? Over here, with this problem that we did before. If you needed to roll at most 2 6s, how would you calculate that probability? Well, how do you roll at most 2? If you roll none, or if you roll 1, exactly 1, or if you roll exactly 2. Right? So this would just be the union of these 3 things. And these three things are disjoint. You can't roll no 6s and exactly 1 6, right? You cannot roll exactly 1 6 and exactly 2 6s. So I could compute that by just adding those things up. No 6s, 1 6, and 2 6s. So it's saying add that number and that number and that number together and it'll give you the answer. By the way, so the problem over there, I mean, we can see they're the same type of problem. Anyway, and fundamentally they're the same type of problem. And this is, they fit under the category of something called a binomial random variable. And if you look ahead to the second section, I think it's the second section, maybe it's the third section, but the first random variable that we'll talk about will be the binomial random, actually it'll be the Bernoulli random variable. And the Bernoulli random variable is just the instance of just doing something once instead of 12 times or n times, right? And then the binomial is n independent Bernoulli trials. It's important enough, right? These sorts of problems are important enough that it's actually the first thing that we end up studying when we start classifying and putting some sort of structure to probability questions, right? And we can see it just comes up in a lot of circumstances. So, what are we going to go do here? If I want to know the probability of a system failure, I'll probably want to add together the probability that, how do I want to, let's let A, K be this failure of K units. So I'll want to exactly K units. And so then I'll figure out, okay, what's the probability that K units fail? What's the probability K plus 1 units fail? What's the probability K plus 2 units fail? All the way up to the probability that N units fail. Okay. And I don't have to worry about intersections because these things are disjoint, right? I can't have exactly K and exactly K minus 1 and exactly K minus 2 and exactly K minus 3. In the same way, I could not roll no 6s and exactly 1 and exactly 2 and exactly 3. And be careful, language, sometimes we'll say roll 1 6, and of course 1 6 would officially mean at least 1 6, right? What's the probability you roll 1 6? Well, you really should use the word exactly 1 6 if you mean 1 6 and no more, right? And you should say at least 1 6 if that's what you mean out of it. So between at least 1 or at most 1 and exactly, be careful with your language and how you read the problems. But these are, I'm going to try to emphasize exactly K units. And so then, what would be the probability of getting, let's see, what would be the probability of getting exactly K failures out of N independent units? Okay. The failures come with probability P, right? Failure 2 comes with probability P. All these failures come with probability P. How do the non-failures come? With the probability of 1 minus P. Right? And so when we have 1 minus P's here. Right. So at the end of this, how many P's have I multiplied together? P to the K. And how many 1 minus P's have I multiplied together?
Minus K.
N minus K, the rest of them. But this was the particular case in which I had the failures were in the first K things. How many different cases are there within that where, of course, the failure could involve the last one or something in the middle? How many different ways could I end up with K failures out of these N units? And choose K. So if I want exactly, or if I want to know the likelihood of exactly K failures, I have N positions I'm going to choose k of them to be the positions for failures. And then a failure happens with probability p, and I'm assuming independence in all of this, so I can turn this into a multiplication all the way through. Okay. So I have this p to the k multiplied by 1 minus p to the n minus k, because once I know k of them are failures, I know n minus k of them are not failures. And if you go back and you let p equal to 1/6, and you let n equal to 12, and then you let k equal whichever one we were trying to calculate, that's exactly what we did with all of those things. Even the first one, right, here, was 12 choose 0, 1/6 to the 0, because I didn't roll any 6s, 5/6 to the 12. Right? Every single one of those fits that same category of how we calculated those things, right? Why does it do that? Because it's a binomial random variable, right? So it's one of those important ones that we really want to understand the problem. Okay? So this one here would be n choose k, p to the k, 1 minus p to the k. What's the probability that we have exactly k plus 1 failures? What do you think is going to change in all of this for k plus 1 failures? Well, instead of having a k here, I'm going to have a k plus 1, right? So it would look something like n choose k plus 1, p to the k plus 1, 1 minus p to the n minus k minus 1, or n minus quantity k plus 1. Okay. So this is how I'd have exactly k failures. Here's how I'd have exactly k plus 1 failures. K plus 2, n choose k plus 2 failures. P to the k plus 2, those are my failures. 1 minus p to the n minus k minus 2. And I'll just keep going until I get to n. And then you say, well, is there a nice way to simplify that? Not necessarily. Not necessarily. But there's a reason why that's called a binomial random variable, right? Because it's attached to the binomial theorem. What does the binomial theorem say? We talked about this not so terribly long ago. Okay. What happens when I take something like x plus y and I want to take it to the power of n? Right. The idea is I could write this as a sum, n equals 0 to infinity, of things that look like, oops, not n, let's make it k. N choose k, x to the k, y to the n minus k, right? And that's exactly what we're doing here, right? We have our n choose k, not x, we're using p, right? P to the k, and then 1 minus p to the n minus k. And then we're going up to the next one, and then we're going to the next one. And, right? So we're essentially doing the same thing, except for here, if we start at 0 and we go off to infinity, then what I would get, right? If I were to add all of these things together, in this particular case, I mean, this with everything that could possibly happen, my n choose k, my p to the k, and my 1 minus p to the n minus k. And if I start at 0 and go to infinity and start at, infinity, there's no infinity, it would go up to n. Right? Go up to n, right? So if I start at 0 and go up to n instead of starting at k and going up to n, then this would sum to p plus 1 minus p to the n. And what is p plus 1 minus p to the n? 1. Okay. Which we expect, right? If I add up everything that could possibly happen, it should add up to 1. Of course, this is not adding all of those things up. It starts at k instead and goes up to n. Okay. Is there a nicer way to write that? Again, the answer is no, not really. If we started at k equal to 1, I'd probably look at the complement of it, because then I would just have to figure out the 0 term, right? But I know if I do everything, it would add up to 1. So depending if this k is really close to 0 or if it's really close to n, I might want to take this so where it's complement depending on it. But this is sort of as nice as it gets. That's why it's much nicer to answer the question, what's the probability of getting exactly 2 6s than it is to calculate the probability of getting at least 2 6s. Because with at least 2 6s, I have to do the same problem 3 times and add them together. Right? Whereas exactly 2 6s, I could set it up in exactly one way. All right, any questions on that or other questions? By the way, this sort of, our combinations, this is a very common way we want to use our combinations, right? When we're counting things, right? We're going to set these things up. Maybe sometimes we'll have independence and we'll say, okay, well, how many ways are there? How many different cases were there in which we end up with something like that? Other questions? Yes.
I had a question a while ago about how in the world the dice rolls all would add up to 1, but you just answered it. And a completely unrelated question.
The dice rolls add up to 1. Which one was that?
Just this question after like the A0 plus A1 plus, all the way to
Oh.
A6, that they add up to 1.
They will add up to 1.
You just answered that.
Yep. Yeah, it is because the binomial random, they're related to the binomial theorem, which means when you add up all of these things up to 12 to 12, 1/6 to the 12th, and 5/6 to the 0, by the time you go through all of it, it adds up to 1. Which is why we call it a binomial. It's nice. Not all of them. There's a geometric random variable that's related to the geometric series. So, so there are certain random variables that are important, and then they have reasonably, you can say what you want about geometric series, but they're reasonably nice in the terms of infinite series. And so then we know how things are summed. There's another random variable we'll talk about, which is called a Poisson random variable, which comes up in a lot of different types of applications. And the terms of the things that we're adding together come from the power series attached to the exponential function, right? We don't have to jump ahead to this yet, but I already said it, so I'm good. So e to the x, does anyone remember how to write the Taylor series? N equals 0, this does actually go up to infinity. What are the terms in front of that one?
This is just 1 over n factorial.
1 over n factorial x to the n. Yeah. Right. And so we'll have things that, we'll have a random variable, something that we're trying to count, that is going to be attached to essentially the terms of these things. Actually, it'll be e to the negative x, right? If I multiply by e to the negative x, and actually let's just make x be now, x, then it adds up to 1. And so if I have this term in front of me, you say, well, where does that e to the negative x, why do we have that in front of it? Because when we end up adding up all the rest of the terms, we get the Taylor series for the exponential function, and it will actually sum to 1. You say, well, why would the Taylor series, why would the terms from a Taylor series have anything to do with probability? Is actually a very valuable one. If you're interested actually in different types of insurance models and stuff, if you want to know how often you expect events to repeat themselves, it will come up in that context. Again, but I don't want to get too far ahead, but we'll talk about those also. Okay. So there are certain ones that definitely tie in with known series or known sums that we have to deal with. Binomial is one of the nicest and easiest and most important of all those. I guess that's it for time. We'll stop there. I did send out an email about RStudio. What I have up here is R in RStudio. If you have a computer of your own and you don't mind putting, we will on occasion, at some point I'll actually talk to you about it instead of just using it for some calculations. Probably the next class I will. I put up on Blackboard this particular R file. So if you don't have it on a computer, you don't have a computer of your own, you can go into the Eaton Lab and you can open up that file. It should open it automatically into RStudio, and you can play around with it a little bit. But it's a nice way to calculate in statistics and in probability to some degree. We will talk about it this time.